Our next speaker is Jean-Gabriel Cuby. Did I pronounce that correctly? Yes. Okay. And he's going to be talking about Euclid.
Thank you. So I'll give this talk on behalf of the Euclid consortium, and more particularly on behalf of the Euclid Primeval Universe Working Group that Sune Toft and I are leading. So this is the layout of my talk. As you know, Euclid is about cosmology, so I'll start discussing a little bit what Euclid will do. Then I'll present the Euclid mission and the survey. And finally, I'll discuss what is more relevant to the subject of this conference, the high redshift universe. So let's start with cosmology. So Euclid is about dark energy. It will map the geometry of the dark universe over the last 10 gigayears. It will investigate the distance-redshift relationship and the evolution of cosmic structures out to redshifts of about 2. And it will use 2 cosmological probes, galaxy clustering, baryonic acoustic oscillations, BAO, and redshift space distortions. And the second probe is weak lensing, or cosmic shear, which allows to map the dark matter distribution and the growth of structures. So this cartoon shows the cone of the universe, starting from the Big Bang, then inflation, and then the matter-dominated epoch when the expansion was decelerating. And today, the dark energy-dominated phase where the expansion is accelerating. So this is basically what Euclid will try to map and trying to determine the geometry of the universe. So this is the principle of operation of the first probe, galaxy clustering, BAO, and redshift space distortion. So the principle of operation is straightforward. You measure the characteristic scale on the large-scale structure of the universe, on the distribution of galaxies, and you do that at different redshifts. And the absolute scale is given by the CMB. This is the sound horizon scale. Given by the CMB data, and the scale is 150 megaparsecs. So by measuring this scale on the galaxy distribution at different redshifts, you get the angular diameter distance as a function of redshift, together with the Hubble constant as a function of redshift. And this allows you, because these quantities depend on cosmological parameters, this allows you to determine the cosmological parameters at different redshifts. So this is the well-known Planck temperature spectrum, and this is the 150 megaparsec scale, which has been observed on the large-scale distribution of galaxies, first from SDSS data in 2005. So Euclid will accurately measure 3D positions of galaxies over this redshift range from 0.7 to 1.8. And for this, it will do imaging and slitless spectroscopy, both in the visible and the near IR. Well, actually, spectroscopy will be only in the near infrared, and this is basically to target H-alpha at redshifts higher than 0.7. So in total, Euclid will measure 35 million spectroscopic redshifts with an accuracy of 0.1% over 15,000 square degrees. So the second probe is weak lensing, or cosmic shear. So as you know, light from a background source goes through a massive structure. It gets deflected, and the image of the source is distorted when we observe it from Earth. So measuring these distortions allow you to reconstruct the mass distribution along the line of sight or between you and the source. So this has been done for decades now, almost, on galaxy clusters. Here is the well-known image of the bullet cluster, and in blue is shown the distribution of dark matter as reconstructed from the cosmic shear. And this has also been done with HST on large-scale structures, and here is a dark matter reconstruction using tomographic techniques on the weak lensing data from redshift of 0.3 or so to redshift 0.7 or 0.8. So what Euclid will do is to measure this weak lensing over the redshift range 0 to 2. So for this, Euclid will require photometric redshifts of the sources out to redshift 2. And this requires visible and near infrared imaging. But the point to note here is that additional data will be required to accurately determine the photometric redshift. So there are several complementary observing programs from the ground at the moment to deliver this data. So in total, Euclid will measure the shapes, shear, and photometric redshift with 5% accuracy of 1.5 billion galaxies over 15,000 square degrees. So here are the top level science requirements. I'm not going to go through all of them. So this is just to mention the main scientific questions that Euclid will address. So dark energy clearly is the main one, and what Euclid will do essentially is to determine whether the equation of state of dark energy is constant and equal to -1, or if there are deviations from this equation of states, and in particular if there are variations with redshift. So Euclid will also test gravity, and it will test general relativity over cosmological scales or alternative gravity models. It will make a census of the dark matter distribution in the universe up to redshift of about 2. And it will also test the initial conditions, and in particular, for instance, evaluate whether these if there are non-Gaussianity in these initial conditions. So here is the Euclid forecast on the measurement of the cosmological parameters. So this is to illustrate the level of accuracy that will be reached with Euclid data. So you see the ellipse errors for the measurements of these various cosmological parameters, and in blue you have the current accuracy on these parameters, and in red is the accuracy that Euclid will reach together with the Planck data. So this is an improvement of at least an order of magnitude on the accuracy of the cosmological parameters that Euclid will achieve. So to finish with cosmology, this is again what Euclid will do. It will really characterize the geometry of the universe and the matter distribution over the past 10 gigayears when the universe was matter-dominated with a decelerating expansion up to today, where the expansion is accelerating under the effect of dark energy. So let me now turn to the Euclid mission and survey. And let me start with the Euclid consortium, which I guess is the equivalent of DPAC as for Gaia, as we've just heard. So the consortium is probably 3 times larger than the Gaia consortium, as we've just heard. The last count was 1,300 members and counting, 15 countries, 125 labs, and 70 members at large, in particular from the US, as NASA is also participating to the mission. So consortium meeting require big rooms. As you can see, typically consortium meetings gather about 400 people. This is probably the largest consortium for an astronomical project today. So some facts about the mission. So this is an M-class ESA cosmic vision mission with a contribution from NASA. It will be launched in 2020 to L2, and this is a 6-year survey-only mission. This is by no means a mission where you can observe your favorite objects. This will be survey-only. Telescope diameter is 1.2 meter. There will be 1 optical band and 3 bands in the near infrared. Pixel scale is 0.1 arcsecond for weak lensing measurements and 0.3 arcsecond in the near infrared. It will provide low resolution spectroscopy in the near infrared with a dispersion of 13 angstroms per pixel. The wide survey is 15,000 square degrees, the deep survey 40 square degrees, and certainly very strong requirements for designing the mission were the necessity to control very accurately, very precisely the point spread function for the weak lensing measurements. So the PSF has to be known very precisely and it has to be stable. And that certainly puts some strong requirements on the mission. There is this requirement on extreme stability. You don't want the PSF to vary with time without being able to control it. Similarly, strong design constraints for the mission were the requirement of controlling the spectroscopic data in terms of purity, in terms of confusion. And another requirement is, as I mentioned already, the need for additional multi-wavelength ground-based data for the photometric redshifts that would be needed for the weak lensing measurements. So here is an overview of the spacecraft and payload module. To the right, the whole thing together, and here is a layout of the optical design. So behind the telescope there is a relay optics feeding the 2 instruments, the near-infrared spectrometer and photometer, the NISP, and the visible instrument here. And there is a dichroic plate, and the 2 instruments are observing together. So in short, here are the main characteristics of the 2 instruments. So the VIS has a field of view of 0.5 square degrees, actually similar to the field of view of the near-infrared instruments. So the VIS features 36 4K by 4K CCDs with 12 micron pixels. Pixel scale is 0.1 arcsecond. The limiting magnitude on the wide survey is AB 24.5 at 10 sigma, and the limiting magnitude of the deep survey is 2 magnitudes fainter, 26.5 at 10 sigma. As I mentioned, there is only one filter covering more or less the OR, I, and Z band. So basically from 550 to 900 nanometers. So for the NISP, the near infrared instrument, there will be 16 2K by 2K Hawaii 2RG RG detectors. The pixel scale is 0.3 arcsecond on sky. The limiting magnitude is 24 AB 5 sigma for the wide survey and 2 magnitudes fainter for the deep. There will be 3 filters, Y, J, and H, and 4 grisms for slitless spectroscopy, 1 blue grism covering the range 920, 1250 nanometers, and 3 red grisms covering this wavelength range. So the 3 red grisms will be used for the wide survey, okay, and the 3 grisms have different orientations. This is to deal with the confusion with the spectroscopic data and purity. The blue grism will not be used on the wide survey. It will be used only for the deep survey. A few words about the ground segment, which of course is a major part of the mission, as Euclid will deliver huge data volumes. It will deliver more than 1 million images in total. The data rate is 100 gigabytes per day. It will, after 6 years, generate more than 200 terabytes of data. Catalogs will have up to 10 billion sources. Of course, there will be heavy processing and simulations. They will also need to combine this data with the diverse ground-based data for the photometric redshift. So in total, it is expected that the mission will generate or use tens of petabytes, maybe up to 100 petabytes in total over the duration of the mission. So this requires a relatively complex organization with 9 science data centers, 10 organization units in Euclid's vocabulary, and 50% of the resources from the Euclid consortium are actually working on the ground segment. So this is a schematic of how it will work. I'm not going to describe this, just to mention that this is the part with the ESA, with the Mission Operations Center, Science Operations Center, and everything in this box is the science ground segment from the Euclid consortium. So all the science data centers are in different countries in the consortium. All right, this is the view of the sky coverage. So basically the wide survey will cover everything which is not in the galactic plane and in the ecliptic plane. So this is represented in green with overlaid on it in dark green here the SDSS footprint, and in magenta in the south the DES footprint. You can see also on this map the location of the 3 deep fields which have been recently chosen or finalized. So one is the north ecliptic pole, straight on the north ecliptic pole, 10 square degrees. Another one is the Chandra deep field south, about 30 degrees from the equator. And the last one, and there will be 10 square degrees also on the CDFS, and 20 square degrees on the south ecliptic pole, at an exact location which still is to be determined. Okay, so let me now move to the last part of my talk, the high redshift universe. So what Euclid will do in relation to the high Z universe is listed here. So we expect to find high redshift quasars from the wide surveys, high redshift Lyman break galaxies from the deep survey, possibly high redshift superluminous supernovae from the deep survey, and there will also be cosmic infrared background studies which encode signatures of very high redshift galaxy populations. So high redshift quasars, again, they will come from the wide survey. They will be selected as Y band or J band dropouts for redshifts higher than 8. They will be selected as this filter dropout at redshift of about 7, but then or there is an issue with the contamination by brown dwarfs. This is represented on this plot. This is O meaning the optical filter of Euclid, O minus Y versus Y minus J, and you have here a quasar track from redshift 6 to redshift 7, and here the locus of low mass stars. And as you can see, the track of the quasars from redshift 6 to 7 is more or less following this locus of low mass stars, and it will be very, very hard to to isolate the quasars or the high redshift galaxies, for that matter, from the brown dwarfs. Whereas if you look at the Y minus J color versus J minus H, here is the same track, and after redshift 8, there is basically no contamination. So just to say that it will be sort of easy to select the high redshift quasars above redshift 8 with Euclid from the wide survey, it will be a quite different issue for redshift 7. So in total, 10 to 50 quasars are expected, of course, depending on luminosity functions that are essentially unknown at the moment at these redshift. And that redshift 7, the brightest quasars will be found directly from the spectroscopic data, okay? But again, they will be very hard to isolate from the photometric data. So this is a simulation of the redshift 7 quasar, the Mortlock quasar, which has been done here. This is what this quasar would look like on the Euclid deep. I think it is on the deep, so it is still visible on the wide survey, and we can see here the carbon 3 and carbon 4 lines. High redshift Lyman break galaxies. So here, what Euclid will do is to probe the bright end of the luminosity function at high redshift. So for the contamination issues that I was mentioning just before, it is highly desirable to have deep Z-band data, but this is unclear whether we will be able to get this data, or at least part of it. So here is represented the luminosity function of high redshift galaxies, depending on, well, different data sets and different simulations or modeling. So Euclid will really probe the bright end of the luminosity function, and no other facility will be able to do so. In spectroscopy, CR7 was mentioned several times during this conference. So CR7 would show up, or will show up, in Euclid in spectroscopy. The Lyman alpha line will show up at the signal-to-noise ratio of 15, whereas the helium-2 line on this object would show up at the signal-to-noise ratio of 4. So just to say that even in spectroscopic mode, some of these objects will be readily detectable. So in total, we expect of the order of 8,000 objects above Redshift 7 down to an AB magnitude of 26. So it happens that these high redshift galaxies are somewhat extended, and this may be another way of differentiating them from local brown dwarfs. These are two images of galaxies with contours of galaxies at redshift 6.7 and 6.8. And here is the most recent calibration of the size-luminosity relation for these galaxies. And basically, in this area, this is what Euclid will probe. And in this area, it will be possible to differentiate between a point-like object and an extended object. So high redshift superluminous supernovae. Here is a plot, light curves of pair instability supernovae at different redshift. This was shown by Daniel Wallens a couple of days ago in this conference. So this is the magnitude, and as you can see, this is above magnitude 26. So these supernovae are unlikely to be detectable from the deep survey, but if there is, at the end of the Euclid mission, an additional deep drilling survey, which is a possibility, this survey would go down to AB 28.5, and it would be able to detect 5 to 10 pair instability supernovae out to redshift of 10. Finally, cosmic infrared background. So this is an image, an IRAC image at 3.6 micron, and after removal of the sources, this is the background and the structured background that is left. So the idea is to do the same thing with Euclid and to measure the power spectrum of the cosmic infrared background, which encodes information on the large-scale distribution of very high redshift galaxies, faint populations that are not resolvable by Euclid. So this work has been done by Kaczynski et al., and there is some hope that this power spectrum can be detected by Euclid with some scaling from what IRAC has detected, and some assumptions on the luminosity functions of faint high redshift galaxy populations. And if that works, that would be really neat, because that would allow to do tomography by comparing the CIB in the different filters, and that could provide a measure of the BAO at redshift above 10. All right, so I'll finish with mentioning other aspects of the legacy science with Euclid. So there is a lot of science other than cosmology that Euclid will do, and other than the high redshift universe science that I've just mentioned. So you have here all the science working groups within Euclid. So in red, in black, these are the cosmology working groups. In blue, the legacy working groups. Some of them also do cosmology, or at least in part. And the working groups, color-coded in green here, are strongly dependent on whether there will be additional surveys at the end of the mission. This is still an open question if there will be additional surveys, and if yes, what these additional surveys will be. So the legacy value can be represented through these numbers and facts that in relation to the Euclid surveys. So again, the Y will generate more than 10 billion sources. 1.5 billion sources will have accurate morphometric information, shape, and photometric redshift. 35 million objects will have accurate spectroscopic redshifts with emission lines, and all over 15,000 square degrees. For the deep survey, again, these are the three deep fields. There will be 10 million sources and 1.5 million galaxies with accurate photometric redshift and shape information, and 150,000 spectroscopic redshifts with the 0.1% accuracy. So here are examples, and these are very limited examples of legacy science that Euclid will enable. This is an image of a galaxy SDSS-like at redshift 0.1. So basically, Euclid will get the same spatial resolution out to redshift 0.7. This is an image of the Sloan Lens ACS survey. So galaxy-galaxy lensing, strong lensing. Euclid will do 3,000 times this survey over the duration of the mission. These are simulated spectra of galaxies at redshift 1.5, and that shows that absorption lines can be detected from the Euclid spectroscopic data. And this is micro-lensing, so if there is an additional survey, micro-lensing studies could be enabled also with Euclid. And I'll stop here.
Are there questions or comments? Can you remind me again when launch is supposed to be?
December 2020 is the...
2020?
Yeah, 2020.
I see, okay.
I can just mention that the schedule has slipped by only 6 months over the last 3 years. So there might be further delays, but hopefully not too long. The mission is pretty much on track at the moment.
Yes, over here.
Do you have any plan to collaborate with other telescope or such as Subaru HSC?
Sorry, can you...
do you have any plan to collaborate with Subaru HSC telescope?
For additional data, you mean?
Yes, I mean that.
Well, there are agreements that are being negotiated or prepared. I don't know all the details. Recently, there is one program that has been accepted at CFHT to cover, I think it is 5,000 square degrees in several bands. So this is really work in progress to try to get agreements with other telescopes to get the ground-based data that will be required for the photometric redshift.
If there's no more questions, let's thank Jean again.